Alright, let's take a look at the warm-up. I'm just going to start it, and I really want you to kind of work through the rest of it. So we have this volume created by rotating this curve around the x-axis. Let's just find the volume of the piece of the object to the right of the line x equals 2. So we have this object. I'll mark out a 1 and a 2. We want to find the volume all the way over here. So I need to set up an integral here. I need to maybe cut a slice of my volume. Okay, what is just the volume of that slice? Well, that slice, if I cut it thin enough, is just a cylinder. So it should just be the area of the top, which is a circle, so I have pi r squared, times the thickness of my cylinder, which in this case will be delta x. So if I want to add up all of those slices continuously, I'm just going to integrate pi times r squared. But what is r in this case? It's just my function. So I have 1 over the square root of x squared minus 1 quantity squared dx. And I'm integrating that from where to where? From 2 to infinity. So that's that integral that should represent this volume. So now see if you can get through this integral. See if you can go through the rest of the integration. Give you some more time to
Will something like this be on the calculator part or the non-calculator?
Even if it was on the calculator part, I would want you to integrate, show all work, and then check your work with your calculator. So this is a good review. It's going to force us to set up a volume integral, which is a nice review. It's going to have us do an improper integral, which is a nice review. And the integral itself might be a little tricky, so that's also a nice review. So it's really 3 topics into 1 question. Good for reviews. I really don't like to do that for actual exam questions. I like to break them into small pieces. But good review question. Started, I'm sure you asked. Can't get started, you should take that as a bad sign. You need some more prep work. All right, I'm just going to do the first couple steps here. First thing I can do is factor out that pi. That pi is just going to sit there for the course of this. But when I square that integrand, the square will cancel out the square root, and I should get this thing. Now, what's the technique I'm going to use on this integral? Is this an elementary integral? Do I just know the answer? I don't. Substitution. Will substitution work? It won't, because remember, I need a derivative I need a function whose derivative is a factor. So if I take the derivative of x squared minus 1, I'll kick out a 2x. I don't have a 2x anywhere. I don't have anything to cancel that 2x. So not substitution. Well, then I got integration by parts, or partial fractions, or trig substitution. Now, trig substitution is kind of hard. I kind of want to avoid that if I can. Integration by parts is usually for a product. I don't see a product here. Doesn't mean I couldn't use partial fractions, but it's definitely not jumping out at me. But I can see that x squared minus 1 can be factored into x plus 1, x minus 1. So then I have 1 over x plus 1, x minus 1. That should be kind of making me think partial fractions. So that's the technique I would use here. So if I'm using that technique, I would be thinking of 1 over x plus 1, x minus 1 equal to a over x plus 1 plus b over x minus 1. And I'll give you some more time to see if you can get to the rest of that. go through the partial fractions here. So we have our partial fraction decomposition. I'm going to multiply through by the common denominator, x plus 1, x minus 1. That gets me this expression. There's a couple ways I can solve this. I could blow this thing all up and organize it into two polynomials, one here and one here, and compare the coefficients. Or I can just choose some good values of x. If x equals 1, well, then this term goes away, and I have 1 equals 2b. So I get my b value. And the same kind of logic gets me the other a value. Any questions about those two pieces? So I'm plugging those values into my integral. So I'm integrating, I'm just going to do the integral over here so I know what that antiderivative is. So this thing is the same thing as integrating this thing. So I'm integrating this, I'm just going to pull my constant out front, that's my a value, and integrate 1 over x plus 1. Pull my b value out, integrate 1 over x minus 1. And then I do both of those integrals. And you can throw on a plus c there as well. Any questions about the integration so far?
Usually those top fractions are like direct natural logs.
Absolutely. I would strongly encourage you to do that. I haven't done that to kind of emphasize the point when we take these limits, but I would absolutely encourage you to do that. This question is, can I rewrite this by factoring out the 1/2 and writing this as a fraction? It's basically natural log of x minus 1 minus the natural log of x plus 1. I can use a log rule to combine those. And that's a very useful thing that we're going to have to do in a second here. I have my antiderivative. Now I'm going to do the improper integral. So once again, this is 3 reviews in 1 for this warm-up. It's, can I set up the right integral to find this volume? That's review number 1. Review number 2 is doing this integration by partial fractions. That's review 2. And now it's, what do I do with an improper integral? So instead of integrating from 2 to infinity, this infinity is the problem piece. I don't know how to do this. So I replace it. Pull my pi out, I have the limit as a goes to infinity of the integral from 2 to a. Now this just looks like a definite integral. I can just do that. And then I'll evaluate the limit when I'm done. So I put in my antiderivative. Now I'm trying to evaluate the limit. I just evaluated it, a and 2. But now I have to evaluate this limit piece. And you have to be careful here because I have, well, as a goes to infinity, what does this thing look like it does? Looks like it blows up. And this one goes to infinity. This kind of looks like it blows up too. I have a negative and a plus. And it's real tempting to say negative infinity plus infinity, that's going to cancel. And we've kind of looked at that before we did improper integrals. And we said, okay, if one blows up, that's it. And that's true if we have different limits. So when we looked at cases before in the past, we said one blows up, that's it. But that's if we have the limit of as a goes to 1 or the limit as b goes to 1. 2 different limits kind of in the same problem. This is one limit. So evaluating these together, I got to worry about whether this is actually going to work or not. It's hard for me to see this here. So what I am going to do is I'm going to rewrite this to be one kind of function. I'm going to use that log property we talked about and look at this as I'll pull out my 1/2 here, and then I have the natural log of a minus 1 over a plus 1. And of course I have my other stuff over here. This one's going to be 0, and this is going to be plus 1/2 the natural log of 3. Everybody see how I combine those two logs? I basically have this log minus this log. Got the difference of logs, I can write them as log of the quotient. Now what happens to this thing as a goes to infinity? As a goes to infinity, what happens to the argument of our natural log? Goes to 1, right? A minus 1 over a plus 1. If a goes to infinity, plus or minus 1 doesn't matter. This is going towards 1. Which means the natural log of something going to 1 is going to look like 0. This is going to 0. And my final answer then is going to be pi over 2 natural log of 3. So even though this thing goes infinitely far to the right, it still has a volume measurement. It still has a finite volume. All right, a lot of pieces to this problem. Any questions? Once again, the value is you working through it and seeing where you get stuck. All right, I could work through that problem in half the time if I just wrote out the solution. All right, but the goal here is to say, where do you get stuck, so you have a gauge of how well you're prepared and what stuff you need to review. All right, plan for today. I take questions from the exam. I also want to talk about an exam policy. I was a little concerned about the time. People felt like they were rushed for the last exam. So what I've decided to do is for this final exam, I will do the exam replacement policy. So if you do better on your final exam than one of your previous exams, it will replace that score. If you do worse than both of your previous exams, those exam scores will just stay the same. Okay? So in other words, if you got a 63 on your first exam and a 72 on your second exam, and on the final you got a 68, when I tabulate the grades, it will look like 68, 72, and 68 for the final. Okay? So we will do a final exam grade replacement. Once again, the biggest idea behind that policy is just that I just want you to learn the material, right? So if you struggled with the first exam or this last one because of time, as long as you have this content mastered by the end, I'm still happy. Okay? Any questions about that? Okay. All right, so we're going to review the content of the 12.3 video after if there's any other questions in the exams, and then we're going to extend those ideas about the dot product to the idea of projection, some physical problems, and just some general practice. But first, any questions from the exam or from the homework or from anything? A chance to look through the key, hopefully, and kind of see if we're to ask grading questions or questions from the key. Yep.
Question 18 was the same. So the function is dx, and then we're trying to find the error value. But in class, we used that one example where you said we couldn't use e, we had to make an assumption.
Yep.
So
what's going on here? So we're trying to find the error bound for our approximation. And we use e to the x centered at 0 as our approximating Taylor series. And we're trying to approximate e to the negative 2. Okay, so our formula for the error bound says the error is less than or equal to the maximum value, we'll call it m. We'll do our m over, we use a second derivative Taylor polynomial, so we should have our 3 factorial. And we have our absolute value of the interval raised to the 3rd power. Right? So this is our kind of our general expression for the error term. So far so good? Okay. Now, m is the maximum value of our 3rd derivative on the interval. Third derivative is e to the x. But what's our interval here?
1, 2.
Why 1?
That's the approximation of the function at e, but it's like increasing.
So m is defined here is the maximum value of the n plus 1 derivative, okay, on the interval from x to a. That interval is from where I'm centered to where I'm evaluating this thing. Yep, or x comma a, whichever, makes sense as the interval here. But where are we centered at in this case? We're centered at 0, but where are we evaluating it? Negative 2. So our interval is from negative 2 to 0. So if the 3rd derivative is e to the x, here's a picture of e to the x. I'm looking for the interval from negative 2 to 0. Where does it take its biggest value? 0. So the largest value for that second derivative occurs at 0, and e to the 0 is 1. So that's why I used a value of 1 in an error bound. Okay? Now, when we did in class, we were approximating e to the square. So our interval was 0 to 2. That's why we use that right-hand side value. Okay? that's the trickiest part of the error thing. You know, we got the formula, so we had note cards, so we have kind of the core of this on here. But really finding that m is really the whole game for the error bound. That's the maximum value of the n+1 derivative on the interval from x to a. On the interval from where I'm centered to where I'm evaluating. Other questions?
So would you then
Yep.
like find that max to sort of evaluate the graph from the derivative or the original function?
There's lots of ways I can do it. Because I know what e to the x looks like, I can just plot it and say, yeah, it's the biggest over here, and evaluate it that side. If I didn't really know what the picture was, I could take the derivative of that n+1 derivative and see if it's increasing or decreasing on the interval. So I could look at the function and say, oh, I take the derivative, and the derivative is always positive in this interval. Therefore, the function must be increasing in this interval. That would tell me the maximum value occurs at the right-hand side. I would evaluate the function over there to find the max value.
So there's the one times like this derivative.
Yeah. I mean, it's really like its own problem. Take that third derivative, e to the x. Now the question, the new problem is, m is the biggest value e to the x can take on this interval. And you can do that a number of different ways. You can plot it and see where the biggest value is. You know, you can make an argument like a trig function. Well, if the third derivative is sine is always smaller than 1, so I can say it's smaller than 1. So, I mean, there's always the chance, not really in this course, but the chance that whatever that function is on your interval might go like this. If that was the case, I would take the derivative, set it equal to 0, do my optimization problem to find that maximum value. All right, does that answer the question? Okay, other questions?
Can you go over 16?
16. Okay. So really it's a step-by-step process for the first one. I have e to the 2x, I know that Taylor series because I know what e to the x is, so I just write out e to the x. Now to go to e to the 2x, everywhere I see an x, I'm just replacing it by 2x. So I'm just really...
That's not what I have for C, or for 16.
Oh, sorry. My number's a little different here. Yeah, I skipped a 15 on my practice one. So you have this one? Okay. My numbering is off on this practice design. Okay. Okay, so the big idea here is we can't use our substitution if we're not centered at the same location. So even though we know the Taylor series for sine of x, we know it centered at 0, not centered at 1. So that was a key point for that lesson, was that if it's centered somewhere else, you got to go back to the formula and chug the thing out. All right, so we have our formula. In general, we could write it out. It's f of a plus f prime of a times x minus a plus f double prime of a over 2 factorial times x minus a squared. Kind of chug out that whole formula. And then we need to find these values. This is the derivative evaluated at a, derivative value a, second derivative value a. So I'm doing that for sine. So I have my function, and so my function evaluated at a, where a is 1 in this case, I'm centered at 1, is going to be sine of 1. So that's my first term. That represents my f of a thing. And then I got to take the derivative of sine. Derivative is cosine. Cosine evaluated at 1 is cosine of 1, whatever that number is. So I have derivative at 1 times x minus 1. And I take the second derivative. It's negative sine of x. I evaluate that at 1. That's my second derivative evaluated at 1 piece. That's negative sine of 1 over 2 factorial. X minus 1 squared. So I'm really just writing out, this is the general definition. I'm centered at 1, so I can write out that. That's me centered at 1. And I'm just finding these specific coefficient values to plug in. And they're ugly for sine. That's why we find sine centered at 0 instead of centered at 1. Because otherwise we don't eliminate every other term, and we have these weird values. Does that answer the question for that one? It's really an application of the definition here.
So when you're centered at 1, you're also using f of 1.
So this is the formula in general for a Taylor series centered at a. So we evaluate the function at a, the derivative at a, the second derivative at a. And if we look at the formula for centered at 0, it's f of 0 plus f prime of 0 times x. because x minus 0 is just x. So we're really just writing this thing out. We're centered at 1, so all the a's turn into 1s. We have to calculate the function, the derivative, etc. And it's really the same thing for this next piece. It's just chugging this thing out. Attached the question. Any questions from the exam?
So once again, as you're prepping for the final now, you're taking your two note cards and you're merging them into one note card. So if that's something you got wrong, put a little star by that definition that you wrote down for Taylor's series. Say, you know, if it's centered somewhere else, I got to use the full formula, not the known series. Whatever notes you need, make sure you add those to your note cards as you go. Other questions from the exam?
The final, the only study guide we have is the exam from last semester.
Sort of. I mean, really the only missing piece is the vector stuff. Okay, and I'm not going to overweight vector stuff. So somebody asked me, a lot of cumulative, it's like 50% old stuff, 50% new stuff. Not so in this case. It's just a representative of the whole semester. So vectors is this last week, so it will be a smaller piece of the final than the other bigger pieces. And we spent much more time on integration, for instance. So there'll be more integration questions there will be on vector questions, likely. At least more points allotted for that. Okay. Yep.
Number 5 was cooling problem. Is there like, if there was like a general formula for that?
So the idea was, you know, it's not that I want you to memorize all these models, but I tried to give you the model in the words. Right? So it's one of those things you have to memorize the formula, or you have to be able to take the words and generate the formula. So this says, Newton's law of cooling, says the temperature of coffee will change at a rate. So the rate of change of the temperature of coffee, that's my rate of change of temperature. It will change proportional to, equal to a constant time, so that's what proportional means. The difference between the temperature of the coffee, so that's T, minus the temperature of the surrounding air. That's my room temperature. So, now I would put on there, use Newton's law of cooling, that's it. I don't necessarily want you to memorize the formulas. I'll either give you the formula or I'll state it in words like this. Okay, so that's that first piece. So your question was, is there a formula for the solution? There is, but in this case I'm telling you to solve for that solution. So let's write the differential equation and then form that solution. And it's actually easier in this case because we have a specific value, so you're not dragging around extra constants. So you really have this piece and you can find the solution and apply the constants, apply the solution. I don't know if that's answering the question. Any questions? Yep.
You have that same answer. Like I would have plugged 60 in essentially for the line. I'm not sure what does that do wrong.
It'll give you an answer, but the answer won't make sense. Okay, so in other words, if we look at this, one thing we can do when we're investigating a differential equation is we can look at the slope field. And if I looked at the slope field for this thing, let's see, if we look at this, is k going to be positive or negative in this case? I mean, just as we look at the problem, rate of change is this thing, do I expect k to be negative or positive? Negative. Why negative?
Cooling.
That's right. If my temperature is bigger than 70, I expect to cool to 70. So I expect this to be negative because my temperature should be changing negatively towards 70. Okay, so I have that negative value here. And really, this is an autonomous differential equation. There are no little t's in here. And so if I wanted to talk about the slope field, I would have an equilibrium solution somewhere at 70 here. So I have straight line solutions on my slope field like this. And if I think, well, what happens if t is bigger? Well, then I have a negative rate of change, so I have a decreasing slope fields. But I know they can't cross that line of 70. Why can't my solutions go like this? And if they cross, I could look at one point there, and then I would have two slopes. I have two slopes at that point. This is a function here. I plug in a value, I get a specific value. So I can't have two slopes here. So I can't cross that line. So all these are going to asymptotically approach that equilibrium solution. The k means that they will decrease down to that solution here, and they'll increase over here. So if you gave me an initial condition that was down here, it would make sense to say, okay, well, if you start here, when will you reach that 60 mark? Well, you'll have some time and you'll be able to find that. So we have initial conditions up here, which means we can't cross over down to find a solution. You can plug in the value and it'll give you some sort of answer, but it won't fit the problem. It won't be right.
So is that why you don't chuck the negatives in front of the k on the general solution?
You can put a k in front of the general solution if you want to start with. That's fine. But whereas I found k to equal natural log of 2/3, you would find k to equal negative natural log of 2/3. So our negatives would sync up when we actually plugged it in. Yep, still work. Yep. All right, so all you're doing there is you're saying, I know that k is going to be negative. I'm going to put the negative there ahead of time, and when I find k, it's going to be a positive value. All right, so you're just kind of putting that ahead of time. Whereas I'm saying k is whatever it is, and in the end I found out, yes, k is negative. The natural log of 2/3 is a negative value. So that's totally fine to put that negative ahead of time. Just don't change it later, right? Other questions? Other questions from the exam? The final exam will look like these two exams. So as I make templates for this stuff, those practice exams are the big master template of a bunch of questions. So all I did was take that practice master, from both exams, package them to one giant LaTeX file, add some problems from an old one that had the vectors in there. I'm just going to blow it all up, I'm going to print it out, and I'm going to pick out which questions I want from it and change the numbers. That's how I make these exams. So there's no surprise on what's on there. Right? You kind of have understanding what we're going to have to do. So a great place to study is with practice exams, the previous exams. Any other questions? Yep. I posted a final, I think, from 2013. So some of it will be a little different, as we cover a little bit different content, but it will have a vector portion on there so you can look through and kind of see what kind of vector questions are asked. It's going to be a lot of vector calculations, like can you add two vectors, can you multiply, can you find the magnitude, that kind of stuff. There might be a vector word problem on there, so you can take that with a grain of salt as well, since that wasn't a focus this course as well. So that's all I'm going to do for practice finally. Other questions? All right. All right, so 12.3 was on the dot product. So hopefully you read the section and watched the video, have kind of an understanding of the basics as we go through this. There are some definitions that we just need to have. So these are the big ideas. We're calling this the dot product because we are taking two vectors, we are multiplying them, and we're going to use a symbol that's a dot product, and the result is going to be a number. U dot V is 10, is 15. It's just some numerical value. Which is another reason they call it the scalar product, because you're taking vectors, you're multiplying, and you're getting a scalar value, a numerical value. There's two ways we can calculate. We have two different definitions. We have the algebraic definition that is just taking the product of each of the components and adding them. So the product of the first components plus the product of the second components plus the product of the third components, dot, 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 dot. That's the algebraic definition. The geometric definition is the product of the magnitude of two vectors times the cosine of the angle in between. So those are all in the videos, and we just need to know how to calculate that stuff. And then for each of these different definitions, there was associated properties. Kind of, what is this actually telling me? And the big geometric properties has us looking at our geometric definition and kind of choosing some important theta values. If we just look at that definition and say, what happens when cosine of theta, when theta is 0, theta is 0 if I have two vectors that are perfectly aligned, like this, well then the dot product would just be the product of the two magnitudes. So specifically, if I looked at u dot u, The angle between should be 0, so cosine of 0 is 1, and the result will just be the magnitude squared. The idea geometrically is the dot product is telling us how well these two vectors are aligned. Cosine of theta takes values between -1 and +1. So the biggest this value can possibly be is 1. Which means the biggest this value can possibly be occurs when theta equals 0. So when these two things are perfectly aligned, the dot product gives its biggest possible value. That's why it's a sense of alignment. Now when these things are not aligned at all, this is when you might think they're not aligned at all, that would be when theta is 90 degrees, then what's my value for the dot product? If I plug in theta equals 90 degrees, what do I get here? 0. Right? So that makes sense. Perfectly aligned, I get the biggest value. I get 0 when they're not aligned. And if they're kind of inversely aligned, I will get negative values. Right? So positive values, 0 value when it's perpendicular, and negative values when they're kind of pointing away from each other. They're negatively aligned, you can almost say. So that's our other big property, is that u dot v equals 0 is true if and only if u is perpendicular to v. And this is one of the most important properties of the dot product. It tells us when these things are perpendicular, when they're orthogonal is another name for perpendicular. The dot product is a measure of alignment. And we have our two definitions. Those are the big ideas from the videos. What's that?
So u dot v, the vectors, is that just times?
Sort of times. What do you mean by times when we talk about vectors? Well, this is how we're defining one kind of times. There's actually two types of times for vectors. This is one of them, so we're calling this the dot product. So this doesn't mean u times v, this is u dot v. U dot product with v. So when dot product equals 0, then they're perpendicular. And this is how we calculate u times v, u dot v. This is the formula for it. Yep.
You said it applies for infinite number of dimensions. That's for parts to the vector itself.
Yep.
Wouldn't it not be linear after like there's 6 dimensions and like I don't.
Well, what do you mean by linear?
Like you can have 3 like at I, J, and K,
Yep.
and it's going to be a straight line. But
Yep.
when you have like 10 parts of that, how is that even going to be straight?
How is the vector going to be straight? I don't know. I mean, I can draw them in 2 dimensions. I can draw them in 3 dimensions. Here's my vector in 3 dimensions. I mean, the vectors themselves. But what does a vector look like in 4 dimensions? I have no idea. I have no idea what that even means visually. But this formula says I don't care what it means visually. I just take the product of their components and add them up.
How does that property still apply if you can't prove that it's...
They look like this.
Well, that, yeah.
For this property, that's the most powerful thing about vectors and the dot product, is that I have no idea what perpendicular means in 4 dimensions because I don't even know what they look like. But this property still means something. What do we mean by perpendicular? What we mean by perpendicular, you can almost relate that to a measure of closeness. So for instance, if I have a line here, and I have a point here, what's the shortest distance from that point to that line? It's the perpendicular distance. Okay? So I talk about vectors, one of the big ideas we're going to learn today is that if I have this vector and I have this vector, I can find this perpendicular vector that goes from here to here. And if I find a vector, I can find its length. So in some sense, I can find that shortest distance. Now once again, I see what that means here, but using these same ideas, I can find the shortest distance between higher dimensional things. Now these vectors could represent price points from a business. And if that's the case,
this shortest distance could be the, the best choice of parameters to minimize cost or something like that. It's going to have a physical meaning that's different but related. And what do I mean by shortest distance? If everything is economics, I usually mean least amount of money. Right? So all those things apply in different physical settings. So I don't know if that helps or not, but so what does perpendicular mean in higher dimensions? Depends on the dimension, depends on what the space is. Okay. Excellent question, though. Excellent question. Any other questions? We'll see a little example of that at the end as well. For now, let's see if we can calculate this stuff. So we have the definitions. You should have seen these in the videos. Some practices. Let's calculate these ones. I have 5 problems. 1, 2, 3, 4 are algebraic, and the one over here is geometric. All right, I have my answers up here. Algebraic definition, we take that product plus this product. So I get 1 times 0 plus 2 times 1 is 2. Next one I get 2. This one I can't do. I'm taking the dot product of 2 things that have to be the same dimension, that have to be the same size. Now, we got to be a little bit careful there, right? This notation says I have a 2-dimensional vector and a 3-dimensional vector. If I wrote 1i plus 2j, right, dot product with 3i plus j plus 4k, and that notation, that missing k assumes 0 times k.
Right, so those are kind of three-dimensional things. That's where you have to assume that there's a 0 here. But this notation does not assume that. This dimension, if there was a 0 here, it would be comma 0, and there would be a 0 at that point. So a little bit careful on that, just the notational issue.
And really, it's not that you see this very often. I'm just kind of being obnoxious and saying, yes, you can't do it unless the dimensions match up. Okay, and then next one. They match up. We can do it even if this is a higher dimensional space. I can just do the algebraic definition. 2 minus 2 plus 1 plus 3 plus 0 minus 4. The result is 0. And the last one is using that geometric definition. I'm just taking the magnitude of the u, that's the length of u, which is, probably wrote that in different order there, 10 times 6, the magnitude of v, times the cosine of the angle in between. I just calculate that stuff out. So any questions about the computational pieces? You absolutely have to be able to calculate these dot products. Now the fact that we have two different definitions is a very powerful tool. It really connects the algebraic to the geometric. It lets us do lots of stuff. One example of what we can do with it is it lets us avoid the geometry. So for instance, this first one up here says that 1, 2, dot 0, 1 is equal to 2. I can calculate the dot product. This is the vector 1, 2. This is the vector 1, 0. There is some theta angle in between. If I wanted to find that angle in between, it would be a little tricky. I'd have to maybe create some sort of triangle, use a little geometry, try to figure out that angle. But I can actually use or find that angle just using these two different definitions of the dot product. Because I know that u dot v by the geometric definition is the magnitude of u times the magnitude of v times the cosine of theta. But I also know that the dot product of these two vectors is 2. Because I can calculate that number geometrically. I can calculate the magnitude of u. U is the square root of 1 plus 4. I can calculate the magnitude of v. It is the square root of 1. And so when I put those two definitions together, I can solve for that theta. Cosine of theta is equal to 2 over root 5. Theta is equal to the arc cosine of whatever. So I can merge these two definitions to find some geometric stuff using some algebraic computation. So that's a nice use of these two definitions together. So the two definitions are powerful because it lets me avoid some geometry. But it also lets me extend my geometry. If we look at number 4 here, this vector and this vector, their dot product was equal to 0. What does that tell me about these two vectors? They're perpendicular. Right? Whatever that looks like in 7 space, I don't know. But that has some sort of physical meaning for this problem, that they are perpendicular. They are not aligned at all. There is 0 alignment between these two things. So all these ideas, not only that, I mean, we already have some sort of relationships here. Magnitude of u, if this is u, I can find its length. So again, I don't know what that means, but I have a sense of length for this thing. I have a sense of perpendicularity. So this vector idea really generalizes well to different spaces. So I can use this geometric property to talk about perpendicularity in higher dimensions. Whatever that means. Okay. Next thing I want to talk about is the algebraic properties. So these were also stated, I believe, in the video. Here we have kind of our standard properties, right? And this is once again to let us know that we can do some algebra stuff with dot products. And so once again, these are just the ones we've seen before, so they have names. What's the name of the first one? That's the commutative property, absolutely. Commutative property. What's the second one? It's the associative property, absolutely. And the last one, it's a distributive property. Distributive. But this list seems a lot shorter than my last list. Seems like stuff is missing, so why? Well, what about this one? How come this property isn't in there? I mean, I got associative property here, but there's a scale in here. That lambda here is just some number. But how come I don't have this thing? I mean, shouldn't this also be true? Isn't that just the associative property? How come that associative property isn't here? Absolutely. When I take the dot product, it's between two vectors of the same dimension. But the result, if I did v dot u, is a number. It's 10. I cannot take u dot 10. That doesn't mean anything. So that's not defined here. So this property is not true. It doesn't hold here. So we just have to be careful when we're dealing with this new area. This isn't times. You can't just apply all the geometry you know for real numbers and say I'm going to throw out multiplication like it's fun. Okay, this is different. This is a vector multiplication that has a specific definition. You also see other missing pieces. I don't have an inverse thing going on here. Well, I can't divide. I'm not just multiplying. I can't just divide by this vector because division is the opposite of multiplication. We're defining multiplication in a very specific way. So we can't do division stuff here until we define something that would mean that or do that. In this case, we're not going to. So our properties are more restrictive here. So these are the properties that we do have. And how are we going to use them? We're really going to use them not to do any proofs or any craziness, but we're going to do them to simplify our calculations sometimes. So for instance, if I have u equal to the vector 1, 2, and v equal to the vector 0, 1, what is u dot v? It is 2. What is 3u dot 15v? Well, I can use my properties. I don't have to actually multiply u by 3 and multiply 15. This property right here says essentially I can factor out my scalars. So I can rewrite this as 3 times 15 times u dot v. Or 45 times that dot product. But the dot product is just 2. So I can just do this as 90. So those are the kind of computations I can do using that property. Another one you'll see quite often is if I have u is equal to 1, 2, and v equal to 6 over the square root of 13, and 7 over the square root of 13. Ugh. I say, what's u dot v? Well, that's 1, 2 dotted with. I know that I can rewrite this. I can factor out that 1 over the square root of 13 to look like this. And now this property of dot product says I can pull that constant out front. And that makes the dot product just a little bit easier to manage and to work with. So now this is, sorry, it's at 13. 1 over the square root of 13 times 6 plus 14. So now I get 20 over root 13. So it's those kind of little calculations now that we can do a little bit easier kind of using these properties. Now the last thing I'm going to say about these properties is that we teach this kind of backwards. It turns out there's this very general thing called the inner product. And the dot product is actually just one example of an inner product. And an inner product can be defined any which way we want to do. If I want to say, here's a vector and here's a vector, and let their inner product be the sum of the first two and product of the second two and divided by 8, whatever I want. I can define an inner product however I want. But it's only really an inner product if I can show that it satisfies these three properties. So any definition I make up becomes an inner product if it satisfies these things. And then once it's an inner product, I can use it to talk about length and perpendicularity. Those are very general things when we work in general spaces. This dot product is one example, this definition for how I defined the dot product. You would start and say, let this be the dot product. And then I need to show that it really is an inner product, so I would show that it satisfies those three properties. And once I have that, then a bunch of theorems come about. Okay? So we're kind of doing a little bit backwards because we're starting with a specific case and kind of getting used to it. But you will generalize it in later classes. Okay. All right. All right, so now we're going to start using the dot product. First thing we're going to use it for is to find projections. Now the video talks about the equation of a plane, which is a very useful thing for Calc 3. We're not going to stress that so much in this course. The main applications we're going to look at are projections and work. So a projection. What is it? Why is it important? And how do we calculate it? Well, let's start out with what is it. Here is a vector v. Here is a vector u. If I imagine some sun, here's my happy sun, there it is, directly above my vectors at high noon, casting a shadow of u straight down, such that it's perpendicular here, then the shadow of u on v is essentially the projection, this vector. So this vector right here, but something like the shadow of u on v, that vector is called the projection of u onto v. This is the projection of u onto v. That's what the projection is. It's that shadow. Okay. As we look at it, it's kind of like it's the part of u that's pointing in the v direction. And that's how we're going to apply it in the physical problems. It's the part of u that points in the v direction. Now let's calculate that piece. So the first thing I see when I look at this is that it's really just like v. In fact, it's just a scaling of v. Right? Because it points in the same direction of v. So it must be, so what is the projection? It must be, what is the projection of u onto v as a formula? It must just be some number times v. Actually, look at this here. Some number times v hat. V hat is the direction, and it's just some number times that direction. And we're going to come up with a formula here as kind of a derivation. But the result has to be some number times v hat, the unit vector. Okay, well, v hat is the vector v divided by its length. We've defined that unit vector before. And this magic number that we need, which is really the length of the projection, your book is going to call that the scalar of u onto v. It's just the magnitude of the projection. It's how long that vector is. We know it points in the v direction, and the scalar piece is going to be an important piece. Is how long this vector needs to be. Now, how do we find out what that thing is? Well, I'm going to look back at my picture here and say, really, it's just this length right here. But I'm going to do a little trig on here. I'm going to put some angle theta like that. And if I want to find that length of the projection, that scalar, I would guess that the cosine of theta must be equal to whatever this number is, scalar of u onto v, divided by what? What is it? Magnitude of u. Right, because that's the length of the hypotenuse. It's the length of that vector u. So we have this thing. So great, now I know what that scalar value is. It's the magnitude of u times the cosine of theta. And that's one formula for this. That is one formula for this. What we're going to see is there's lots of different formulas for this projection piece. Some are useful in certain situations, and some are useful for others. So that's our first formula for the projection. Now I'm going to do a little bit of weird algebra. I'm going to multiply this whole thing by 1. I'm allowed to do that. It's not changing the value. But 1 in my case is going to look like this. Weird one, right? So y. Now when I multiply these things, if I multiply these denominators, I will get v over the magnitude of v squared. I'll just leave that over here. Yeah. I have the 2 magnitude of v in the denominator. When I take this numerator and then multiply it through, I get the magnitude of v times magnitude of u times cosine of the angle in between. What is that? That's just the inner product. That's just the dot product. That's just the geometric definition. So that top piece becomes u dot v. So that's maybe a better formula for the projection. Now a formula you'll see is kind of like this. Of course it's equal to it, but you'll see in your physics courses or in calculus 3 is if v over the magnitude is the unit vector, and because this is just a number, we have that property that says that I could pull it up front, or I could put it in front of the first one, or put it in front of the second, I can put it wherever I want. I can think of this as u dot v over v hat, or v over the magnitude of v. So I could rewrite this as u dot v hat times v hat. So sometimes in physics applications, Calc 3 applications, you'll see that version as well. The last version I'm going to point out here is if I multiply these 2 bottom magnitudes together, I would get magnitude of v squared. But magnitude of v squared is just equal to v dot v. So the last way I can write this is u dot v divided by v dot v times the vector v. And the nice thing is that this one is easy to calculate. All right, just 2 dot products, and I throw in the vector v. So this is probably the easiest one to calculate the projection with. The other, probably the second most useful one, would be this one. And why is this one useful? Because this piece is the length. So if you want just the length of the vector, u dot v divided by the magnitude of v, as this is the unit vector. So this highlights the fact that we have the length of the vector times the direction. So sometimes that's useful. And this one's useful just because it's much easier to calculate. You don't have to actually calculate a unit vector at all. All right, so that's our definition. I'll let you try one. If you see the answer right at the top. I did my calculations up there. Any questions about those calculations? Any questions about the mechanics? Am I surprised by the result? You can kind of guess that, right? If I project down onto the x-axis, I should just get the x component. And that's what I have here. What do you expect if I projected along the y-axis, what I would get? Get the y component. And together they make up the vector. Now more generally, instead of projecting onto the y-axis, you can almost think about that as projecting onto something perpendicular to the x-axis, not the y-axis. But the idea is when I project down, I am finding this vector. And u is really made up of two vectors. It's the sum of this vector and this vector. One of these is parallel to the x-axis and one is perpendicular to the x-axis. And being able to break down a vector into these two components is a very useful thing. So I can find this vector as the projection of u onto, in this case, v. But oftentimes I want to find out what's left. What I've done here is the projection is the amount of u that is pointing in the x direction. But what's left? Well, the rest of the stuff is just the piece that's perpendicular to this. Now, once again, I could project onto the y-axis to find this, but I don't have to. There's actually a much easier way to do this. Anybody see the relationship between these three vectors that I've drawn? What's the equation I could write? What is it? I could use Pythagorean, absolutely. But there's a problem with that, a limitation of that. That just deals in magnitudes. So I can find the magnitude of this, and the magnitude of this, and so I could use these two to figure out how long this one is, but I don't have a good sense for the direction. I mean, on here, it's the y direction, right? But if it was something different, something I couldn't see to say, oh yes, I know what the direction is, I would just have the number using Pythag. I want to get all the information, the length and the direction. I want to get the vector. If I know this vector, and I know this vector, how could I find this vector? How could I find the vector that points from this one to this one? Subtraction, absolutely. You can almost think about it as addition too. These are tip to tail, so this plus this should get me this. But we want to use the subtraction here because we know what u is and we know what v is. This one just has to be u minus v. That will get the vector. I'm sorry, not minus v. That would give me this vector. This is u minus the projection of u onto v. And because this is my projection, and I want a vector that points from that projection vector up to u. And so if I did that, if I took the vector 5, 3, and I subtracted my projection, which is 5, 0, the result is 0, 3. And that really is that vertical vector. And it's really perpendicular to v. How do I know it's perpendicular to v? How can I show that it's perpendicular to v? If two vectors are perpendicular, what's true? Cosine of theta would be equal to 0, because it's pi over 2, absolutely. But I don't know, I'm hoping this is the right triangle. I'm hoping these are perpendicular. But I need to show that it's 90 degrees. So what do I need to do? How do I show that this is perpendicular to this? Take their dot product. Their dot product should be equal to 0. If I take 5, 0, dotted with 0, 3, I get 0. So those two vectors are perpendicular. And of course they have to be. That's how I constructed them. Now, this is kind of trivial in this case. I'm projecting onto the x-axis. I know that one's the y-axis. I can see all that stuff. But in general, this is going to allow me to take a vector u and break it into two pieces. One that's parallel to another vector, and one that's perpendicular. I'm resolving this vector into different components. This is generally a very useful thing. So we went through that last example. This is kind of the generalization of this. If I have u, I can find the projection of u onto v to find this vector. And your book is going to call this n for normal. It's the normal component. Normal is perpendicular here. So the normal component of u is the piece of u that's perpendicular to v. We just get that by taking u minus the projection. So if I have a specific u and v, I have a formula for the projection. I can find that projection vector. And to find this perpendicular piece, I just take u minus the projection.
Can't there be a number of normal vectors?
What's that?
Said, can't there be an array of normal vectors?
We use normal vector in a lot of different ways. That word normal just means kind of perpendicular. So for instance, if I'm talking about the normal vector to a plane, if I have a plane, I have a vector that's perpendicular to it, there's two of them, one up and one down. If I said, here's a line, find a vector normal to this line, there could be infinitely many as I just swing my pencil around it. So in this case,
How would you calculate it?
what's that?
How would you calculate it?
There usually would be a variable somewhere in your calculation. So you do the calculation and you get 3x, comma 2, comma 1, right? And so that's a normal vector for any value of x. So yeah. Now in this case, this projection is going to be unique. I mean, this normal vector is going to be unique in this situation because we're looking for something that's not only perpendicular to v, but the sum of this and this give us u. So that's like the extra piece that really restricts if there's only one of these things. Okay? All right, let's try this. There's u, there's v. First of all, the first question is what's the dot product? That's something we can calculate. Just take a second to calculate that dot product. What is that dot product? This times this plus this times this. So my dot product should be 20. And then it has a weird kind of phrasing in the question. Represent u as the sum of a vector parallel to v and a vector perpendicular to v. That's just an annoying way to ask this decomposition piece. It's saying find the projection of u onto v. That's this piece. That's the piece that's parallel to v. And then this normal vector is going to be the piece that's perpendicular. So first we have to find the projection of u onto v. Apparently I should be cleaning up. That's the expression. Any questions about that? I have that n. If I were to take that ugly n, and take the dot product of that thing with the projection, what would I get? If I took this thing and dotted with this thing, what should I get? If I take this thing, dotted with this thing, what should I get? 0. So that should work out. That should be 0. They should be orthogonal. If I take this thing plus this thing, what should I get? If I take this thing plus this thing, u. Yep. Because this vector plus this vector get me this vector. Okay. All right, application problem here. We'll just go through what we need to do. We won't do the calculation. A canoe is moving with a velocity given by that vector, 5I plus 3j. So this velocity vector is 5, 3. The velocity of the current in the water is given by this. So now we have a current vector, and it is 1, 2. These are velocity vectors. First question is, what is the speed of the current? If I'm given the velocity vector, how do I find the speed of the current? The magnitude. So this is just the magnitude of that vector. That's just the square root of 1 squared plus 2 squared, root 5. The second one says, what is the speed of the current in the direction of the canoe's motion? What is that thing asking me? What? Absolutely. It says, this is how fast the currents go, but that's not all the stuff that's pushing me. And some of it's going in the wrong direction. I want to know how much speed is helping me, and how much of the current speed is actually pushing me along in the river. So if I know that, we got 5, 3 here. That's 5, 3. There's my canoe, but my current is like this. How much of the speed is in the direction of the canoe? I got to find this vector and find the speed of this vector. So I got to calculate the magnitude of the projection of C onto V. Okay. And magnitude because they're saying speed. So this is really just the scalar of U onto V. And in general, if I wanted the vector, say how much is this actually pushing me, I would just find the projection. Yep. Question?
And then find the magnitude of the resultant vector.
That's a different question. That's like, where's my, in this case, it says this is how my canoe is traveling, which means I must be paddling like somewhere down this way and pushing me in this direction. Yeah. So this is taking that into account. This is where I'm actually going, and this is just kind of a related question, saying how much is the speed going to be. So you would use this to say, okay, how much force is really from the current is really pushing me. And I might need that to figure out how much work my engine is doing. Something like that. Okay. The next topic is going to be work, so I'm going to start class next time with a discussion about work. We'll kind of go through that relatively quickly. And then my last example was just higher dimensional, so more of a real-life application of what higher dimensional vectors might look like. What would a dot product look like? But for tomorrow, we start beginning the homework at 12.3. It's a lot of calculations with the dot product. And read section 12.4. There is a cross-product video, so watch that video and prepare for class. And office hours is right now.